Okay, so today I'm going to finally talk about this modification of our basic multiple server queue. And what this one does that the other ones haven't is that we're going to model each customer as its own entity. In addition to that, we're going to have each customer carry around their own service time. And then on top of that, we're going to model the servers individually, something that we haven't been doing before. And that's something that's important to realize is how you define your state variables is more or less what an indicator of the kind of information or data that you can get out of it. So when we only count the queue, our customers in the queue as a count, then we can do things like estimate the average number in the queue by using the time average means that we've been talking about. But we can't identify explicitly what the individual times in the queue or the times in the system are for those customers. And as we saw, when we then transition from just counting the customers to representing them explicitly with these entities, then not only can we actually directly get these times for the customers and thereby directly estimate things like the average delays, we can also make our model a little bit more flexible. So for example, when we move the service times from the server to the customer, then that enables us to, in a more straightforward manner, abstract where these service times come from. In other words, if we're dealing with a heterogeneous customer population, then it's a little more straightforward to have the customers hand us their service time when they come, rather than have the server be responsible for that. Now and then in certain models, like in that reneging model that I had you do, and I'm in the midst of grading, with that reneging model, there was an example where we needed to have explicit representation of the customers because we didn't know, for a given customer, before they made it to a certain part of the system, that is, before certain events occurred, we didn't know whether a given customer would get service or whether they would leave. We just didn't know that. And so in that model, you pretty much need something like entities in order to do the business. Now here we're moving on to the servers, and the assumptions that we've had up to now, when we've only been counting the number of servers, that enables us to do things like estimate the average utilization over all the servers. But because that implicitly treats the servers as being homogeneous, that is all the same up to a probability distribution. In other words, our assumption up to now has been that every server has the same distribution of service times. And even when we had two different types of servers, each type of server, even when we had multiple number of them, they still all had the same service times, the same distribution of service times, not necessarily the same number. And then, in keeping with our iterative approach, if we look at our system and we notice that actually our servers are not homogeneous really, but they're heterogeneous, what is it that makes one server different from another in the context of our highly abstract model here? And one element of that is what I'm calling the efficiency. That is, for a given customer who has a given amount of work that needs to be done, one server will get it done more quickly than the other. So is it clear that that's a little, in a situation where we might have a significant disparity between our different servers, that might be something of interest? Hello? Okay, so our models up to now have not been able to capture that. So that's what we're going to capture here. And then in the process, we're also going to see how array states are, what array states are about, and in particular, as we've already kind of seen, but we're going to see again, instead of property change events, when we have states that are arrays, in 99.9% of the cases, it's going to be only one index of the array state that's going to be changed at any given time. And so the way that we deal with that is something called an index property change event. And that's really more on the implementation side. In terms of the event graphs themselves, the implicit assumption is that there is some mechanism to listen for the state transitions and somehow do something in order to get the kind of measures that we're interested in. Okay, so the idea here is that every server has an efficiency and every customer has a processing time. And so there are a number of different ways of doing it. And so the idea is that if a customer comes in, they have a processing time, which means for that customer, there is a fixed amount of work that they need to have done. And when they're being processed by a server, their efficiency, like if a server has an efficiency of 1, then it will take exactly that amount of time in order to get it done. So if a customer comes in and they have 1 hour worth of work and they're being processed with a server with an efficiency of 1, it'll take them 1 hour. If the server has an efficiency of, let's say, 0.5, then it'll take them a half hour. So just the way that it's modeled, and you could go either way, so do you want to multiply or divide? So multiplication is easier and faster than division, so we're going to multiply. So what that means is that if you are a server and you're more efficient than, quote, normal, then you'll have an efficiency that's less than 1. But if you're less efficient, you will have an efficiency that's greater than 1. So if I am a customer and I have a processing time of 1 hour and I'm being served by a server with an efficiency of, say, 1.5, then it'll take an hour and a half instead of an hour. Okay, so what this gives us is a much more expressiveness in terms of how we can represent stuff that's about here. So, what is it that causes the processing time to be greater or less than? Well, it might be if we're a fabrication shop or something. If we're a machine shop, then we may get jobs of different sizes. And our machines might have, we might have newer, faster, zippier machines, and those would have efficiencies less than 1, say, and then we might have older machines that have a greater efficiency. So the idea here now is that unlike, instead of just having one, we have the actual time it's going to take to process a given customer is going to be the product of the two. The product of how much processing time the customer requires and how efficient the server is. Okay, so to model this, we are going to use entities for both the customer and for the server. So so now our customer, and this is in the renege model. The customer had both a processing time and a renege time. Now here we're not dealing with reneges yet. If we were, then we could use the customer from the renege model. But here we're in this context we're calling it a customer too. I think in the implementation I have to call it something a little different to distinguish it from the renege one. But again, it will subclass our entity, so it carries around all of the capabilities of an entity. So in particular, the timestamp, which is what its default comparator uses, and then it carries around just a processing time. So again, we've moved the processing time or the service time from the server piece to the customer, and this is what we've been traditionally calling T sub S for service. And now, similarly, though, now we're going to have another subclass of entity. I'm going to call it a server, and it's going to have an additional attribute called efficiency, which in the event graph I'm going to call G, just for simplicity. Again, just to comment on names here, is like when you're writing a program, you want a name which is as descriptive as possible without being too German about it. When you have a mathematical model, and event graphs are actually mathematical models, then usually you have shorter, smaller variables. So in math, when you have equations, you have x, y, and z, and all that sort of stuff. You don't have big long names. But if you're looking at a program and you see variables called x, y, and z, I mean that's going to drive you nuts, because what the heck is x? Like that meme says, dear algebra, we don't know where your x is, and we don't know why. Okay, so let's look at the server component. And so now we're down to just one parameter, and it's going to just be an array of the server instances. So remember, the parameter is something that doesn't change. In this model, we're not worried about things like failures or breaks. Our servers work 24/7 without a stop. And so we need, in the previous models, we simply said this is how many servers we have. Now, because we're modeling the servers as entities, we need to have a fixed set of them. And this could be an array, or it could be a container. I chose an array, just, again, that's a lot of just understand, a lot of these are choices. They're not laws of nature. So state variables, and we've seen our delay in queue and the time in the system, so a model like this can handle that. We've seen in this case, a FIFO container of waiting customers, and it's initially going to be empty. But now we're going to have a container of all available server entities, and initially it's going to contain every server instance in the all array. Okay, so we need a way of we need a way of making sure that happens. Okay, so here's our component, and again, um, we see two patterns that are that should be kind of representative. In the case of our my mouse, they make my mouse disappear. I don't know why. Okay, so in the case of our initializing our server entities, we have this array of all the server instances, and so at the very beginning, we need to make sure that they're all in the they're all in that container. Now, if the parameter had been a container, then we could do something in the run event like add all or something like that. But just to be ornery, I made it an array, and as an array, I can't add all of an array into a container just with one. I mean, I can do it with a little dance in the implementation. But again, just to see again what the pattern is. So we've seen two patterns that are like this, say with say a run event followed by a self-scheduling edge, and they are different. It's important to understand the difference. The first one we encountered was the arrival process, and there the self-scheduling edge of that event had a delay on it. Whereas for the event graph version of the for loop, there's no delay. It all happens, it basically spins with zero delay, and in this case it spins at time 0 until it's all finished. And that's the second difference. Okay, so there are two patterns that look like this, this top piece. One is the arrival process, and the second is the for loop that we've seen. And as we have seen, this pattern shows up a lot, especially when we have state variables that are arrays. Now at the bottom, we see another pattern we've seen almost from the beginning, which is this: we have an event that schedules another event, and then it schedules a third event, but then the third event schedules the middle event again. And that's another common pattern. So even in a model that's more complex than this, we've seen this kind of pattern embedded in there. And this is fairly common. In any situation where you have some kind of resource, like servers or machines as we've been calling them, and you have to queue up for that, then you will see a pattern like this. And it won't always be exactly like this. We've seen many different variations of this, but this is a common pattern that we see. Okay, so looking at how, oops. Darn. Okay, so I don't know why it makes my mouse disappear, but okay. So we have an arrival of a customer. The argument, called it E here. I've called it C other place. Again, just like with a method, the name of the argument is just it's just a formal argument. In other words, there is nothing special about that other than you're just labeling what that argument is going to be. So when an arrival event occurs, it's going to be one of these customers. And as we have done before, we're going to stamp its time to make sure that we know when it arrived, and then we're going to add it to the queue. Now, under certain conditions, we can begin service upon arrival. And in the past, that condition has been something like s bigger than 0 or s bigger than or equal to 1. In other words, the English translation of that is that there is an available server. So in the language of this model, the way we say that there is an available server is that the container of server entities is not empty. And that's what this says. This. Can't even, let me try to restart. Okay, so our condition is that the container of server entities is not empty. And under that condition, we can schedule the start service. And again, been kind of wondering about you were asking about the priorities, high priority. Yeah, normally in this context, we want to schedule the start service with a high priority. If you don't do that, and you make sure that all of your probability distributions are continuous, then there's really no harm in that. Okay, so now in the start service event, in the past when we have used customers as entities, we've popped it off the queue and then kind of saved it in a local variable here. In the past models, when we were only counting the available servers, we would simply decrement the number of available servers. But now what we're going to do is we're going to pop off a server from the available servers. And now, because for our customer, as we have done before, our elapsed time for that customer that we've just popped off is the time that they have spent in the queue. Now, kind of moving on to and again, we're not going to look at, I'll deal with the scheduling edges on these a little bit later, but now, so here's the thing on the end service event. Okay, there are two things. One is, if we want to estimate the time in the system, then we need to know which customer we're finishing service on. And well, pretty much the only way to do that here is to pass it as an argument. The only way is a little bit extreme. There are other ways to do it, but they're very clumsy. The most natural way is to pass the customer that we have started service on to the end service event as an argument, and that way the end service event knows which customer has completed service. And so their elapsed time is the time between that customer was an argument at the end service event and when they were an argument at the arrival event. That's how long they've been in the system. And we've done that before. But now, remember in the past, we could simply increment the number of available servers, but we can't do that now. We need to know not only which customer did we complete service on, but which server did we complete service on for that customer. We need to know both of those things in order to fully implement this state transition for the end service event. In other words, what we need to do is when a server has completed service, we need to put it back into the list of the container of available servers. And now, since the end service event now requires 2 arguments, that means that we must pass it 2 arguments. I need to, Okay, again, this is something which is critical because there's no compiler to make it off. So if we're doing this with pencil and paper, we have to be the compiler. So end service event requires 2 arguments, so we must pass it 2 arguments. And so just be clear about, the notation is that the parameters that are passed are put in a little box on the scheduling edge. So whereas the priorities are in like a little circle. So how do you know if it's a parameter or a priority? If it's a circle, it's a priority. If it's a box, it's an argument.
So when you're designing the notation for this, why'd you go with like just an H, or I'm assuming it's like a low priority than L, like instead of just having it be a numerical value?
Tradition. I mean, this is just sort of the common it's just sort of a standard they use. You know, there's a predetermined set of priorities. Actually, there's the default one. There's high, higher, and highest, and low, lower, and lowest. There are the predetermined ones. In SimKit, actually, you can set your priority to be whatever value you want. So, but
So it's
in
just notational tradition for the graphs.
yeah, no, yeah, the notation on this comes from the guy who invented these. So, pardon me? The person who invented this was a person named Lee Shrubin, and he was a professor at Cornell, and then he was a professor at UC Berkeley, and then he retired a few years ago.
Is
So
he still alive?
yeah.
Take it up.
So all complaints should be directed to him, but and since he's retired, he may not care anymore. I don't know. I mean, he was a minimalist. He actually resisted some of these additional features, but when he put them in, this is how he put them in. So I follow that. Which doesn't mean that they're the, you know, I think if there's a better way to represent this, as I'm sure there is, that would be an improvement. But this is basically what it is. Yeah, and he, this kind of drove me nuts a little bit. He liked this little squiggly, this S-shaped squiggly thing. So that's what he did. And it was a bit of a pain to create one of those, but anyway. Okay, so but it is important to have a match between the parameters and the arguments on the events. So that's the case here because end service requires 2, and so we're passing 2. But when end service schedules start service, it doesn't pass any. Why? Because start service has 0 arguments. And so every time you schedule it, there must be exactly 0 arguments. Now the arrival event here, it has an argument, and it is not scheduled by anything. It has to listen for another event. And what that means is that the event that it has to listen for must have an argument in it which matches what this is. In other words, this has to be a customer object, thing, entity, which is in the arrival. And we'll see that in just a second. But the main thing here is the way that we're implementing the server efficiencies are right here. And what this is remember that the just sort of a naked number or variable on a scheduling edge is the time delay. So if one is absent, as there is here, from end service to start service or arrival to start service, if it's missing, it means it's 0. But if it is here, if there's just a number slapped on the scheduling edge, then that's the delay. And again, that's from Shrubin's notation, so blame him. But here, the delay, okay, so now how much time is it going to take when we have a customer E and a server S? Well, customer E has a processing time T sub S, and that comes from their attribute. So that's how much work that customer requires. The server has an efficiency of G, and again, the way this is being modeled, an efficiency of less than 1 means it's going to go faster. So the total time that it's going to take to process this customer with this server is going to be the product of the customer service time and the server's efficiency. Okay, so if the same customer gets a zippy server, then they'll get out sooner. If they get a slow server, it'll take them a little longer. Okay, so basically that's the one additional thing. Now, as I said, we need to have an arrival event, a sequence of arrival events that have a customer in them. Now, in our customer, again, since this only has a single attribute of a service time, we need to have an arrival-like process. But now we need to have an inter-arrival time because we need to produce our sequence of just sort of basic events, a stream of events, and then we need our processing time. And so the arrival event, the plain arrival event, is going to instantiate a customer and then schedule an arrival event with that customer as the argument. So again, here's the parameter being passed in the box, the argument being specified with in the parentheses. And then, so we could write this from scratch, or we could do it the lazy way, which is just to subclass our arrival process, override arrivals, making sure that we call the super, instantiate the new customer, and then schedule the arrival. And so with either one of these, if we have our customer arrival process and our server, then if the server is listening, then listening to this customer arrival process, it will hear this arrival event with a customer as an argument, and then that in turn will trigger this arrival event here. And since there are no other events in, so we have because when we do a sim event listener, we're hearing all of the events except for run. So if we are listening to a component that has, say, a start service event, and we will hear that. So you need to be mindful of that. In this case, it's okay because there is the only event of interest. The only events that are being scheduled here, in fact, are arrival with no argument and arrival with an argument. And so the server component is going to hear the arrival events with no argument, but it's going to not do anything about them because it doesn't have an arrival event with no argument. But when it hears an arrival event with an argument, then it will respond to it in kind. Okay, so just to okay, I want to come back to this. In fact, I may have to delay on that for tomorrow. And let's see. Well, let's see. Okay, so yeah, here, let's see. Because there's going to be a customer for the Renee, I called this customer with service time. So here's how we extend the entity. Again, very straightforward. Oh, darn. I forgot to push the one with the, yeah. There'll be an update where I actually have comments. I want to set it better. Okay, so so basically, again, now with entities, there is not, the entities don't have to have a zero argument constructor. In fact, it probably is best if they don't. It doesn't hurt. I mean, it doesn't really hurt either way. But okay, so we have the service time for the customer, and again, we want to make sure that that service time is well, at least 0. And so now we're allowing the fact that there could be a service time of 0. Should there be an equal sign here? Maybe. But certainly a negative service time is going to make things off. Okay, so here's our server, and I say server with efficiencies. So our server with efficiencies we're going to give it an efficiency, and again, the efficiency cannot be less than or equal to 0. So if you have an efficiency of 0, the way that we're working this, if I have a server with an efficiency of 0, then how long is it going to take to, basically that means that I'm going to do it instantly. So that, if I have a server with a negative efficiency though, what's that going to do? That's going to, again, scheduling edges have a delay that says this event is going to be scheduled this much in the future. What happens if I put a negative delay on a scheduling edge? It goes into the past. So, and will
SymKit handle that, or will it just ignore it?
That will be an error. The event list says if you try to move time backwards, that's obviously going to be an error. Because if you have a model in which you are allowed to move to schedule things in the past, then you're assuming that a time machine has been invented, and so far it hasn't been. Now, according to some physicists at least, it's theoretically possible to have a time machine, but so far nobody's actually made one except in movies. So, so a negative delay will produce, the simulation will bomb.
If you're modeling like a network environment, I could see where that might be something you'd want to do, where let's say because you don't know if an event got lost or something like that, but you know that certain events might depend on others. Like if your tank got damaged, there's an event that was like caused that damage somewhere down the line. Or missile impact would imply there's been a missile fired somewhere down the line, and it might be, if you weren't trying to maintain some sort of local state, it might make sense to have the ability to kind of push stuff in the event history at least.
Oh yeah. Now the context for that are in distributed simulations where I have different processors, different machines that are actually running the same simulation with their own event list. And what you say is exactly what happens. What tends to happen in that case is because I have events going on in different machines, then the tank in one that destroyed the other tank in this model was actually destroyed 10 minutes ago in this other process here. And so what those models have to do is they have to actually be able to roll back time and undo the events, because what will happen there is that all of a sudden you realize that, okay, something happened in this process that affected an entity in this process in the past that negates what could have been done here. And so what everybody has to do, everybody in the federate has to now roll back all of your events, undo all of the state transitions back to when before things happened, and then try to redo it like that. But that only occurs in a distributed environment. If I have one event list that's handling all of these things, then it doesn't show up because everything is just sort of one thing here. But that's definitely something which does occur. So so here again the arrival process, the customer with service time arrival process. The names on this drove me kind of nuts. So the thing to remember on these is that when we subclass. So here we're subclassing the arrival process because Java doesn't automatically create constructors for you. You have to explicitly do that, And then any parameters which are in the superclass, you also need to be include in your master constructor. So specifically here, because we are extending arrival process, and arrival process needs an inter-arrival time generator, we need to pass it here, but we do not declare it again. If you declare it again, then if I were to declare inter-arrival time generator again here, then the one in the superclass is not. It's going to shadow the one in the superclass, and it won't be working right. So let's see. Is this, what is this? No, that's something else. All right. Okay. So let's look at the. I think I have time to. Okay. So here's our called queue with server efficiencies. So here's my array of these servers. Here's my set of available servers, and I only declared that to be a set because we might want to have different ways of pulling the servers out. What was the basic model here, the one that I'm implementing, is going to use just rotate them. Give me first in, first out. So every time a customer shows up, it's just going to pull the top server. When you finish, it's going to put it on the end and rotate them like that. Is that the best way to do it? Well, that's something that we could address if we were to instantiate our set of servers with different priorities. So for example, I might, instead of the default comparator for these, I could create a custom comparator and have it say, put the fastest machines at the top. So the ones with the smallest efficiencies would go to the front. So every time a customer wanted a server, it would pop off the top, and the top would be the server that had the best efficiency. That's not what this does. What this does is this does first in, first out. Okay, so here's our queue. And again, in situations like this where we have state variables that need to be instantiated, the preferred way to do that is to instantiate them in the zero argument constructor and then call the this. Again, why the zero argument constructor? Two reasons. One is to conform to the Java Beans specifications, and then the second, the more practical one, is that if we're going to instantiate this from an input file, then the most effective way I've found to do it is to first instantiate the component and then inspect it in terms of what parameters it expects. And that's why you want to have setters and getters on the parameters, because that's going to tell any one of these configurators which parameters are necessary, and it will also allow you to say, okay, maybe where you're missing a parameter. Okay, so here, let's see. Oh, drat! I forgot to push the comments, so there'll be an update with the comments. So again, here's the init. So I'm going to add the ith element to the available servers. I'm going to fire the property change, and what I'm going to call it now is the server busy. So the server busy is going to be either 0 or 1, depending on whether it's available or busy. So a server busy of 0 means that it's not busy. Okay, so here's the arrival event. Again, we stamp the time, we add it to the customer, and then, okay, so what, all right, I was being lazy here. So here, I decided not to do the old value and new value. So that's definitely, I see I uploaded the wrong one, but okay, so here's the, here are the things. Okay, so here, when I pop the server off, I'm going to fire an index property change. The index is going to be the ID of the server, and its value is, in this case, is going to be 1 because now it is now busy. So here's my, when I schedule the end service, here's where I take the product of the service time and the server's efficiency, and then here's where I pass the server and the customer to the end service event. So the end service event has a server and a customer as its arguments, and that will work because my wait delay had both the server and the customer. And now again, my server busy is now 0 because it's now not busy. So let's, okay, so here's how we can run this. For our service time generator, again, these should look fairly familiar parameters, but again, our values are going to be different because it's being run slightly differently. So our arrival process for the customers is going to have our inter-arrival time generator and a service time generator. So here I have 2 servers, one that's kind of fairly fast and one that's kind of pretty slow. And again, how would you encounter something like this? Well, maybe this server's been working there for a long time and is really fast at it. Maybe this is a new hire or an intern who is just learning how to do the job. And as time goes on, maybe their efficiency will get better. But for our purposes of our analysis, this is kind of where they are. So we instantiate it. So our number in queue, again, we can use this collection size business. We can use a tally for delay in queue. And then, okay, so now for our servers, remember we were firing an index property change event where the index was the ID of the server, and we were calling it server busy. So now if we collect that with a time varying, that will give us the utilization for each server. So, and okay, I can see I uploaded the wrong ones here. So this was kind of didn't have the full Monty, but it has at least sort of enough. So, and as you see, even this one, we ran it for 100,000 time units. We got the average number in the queue and the average delay in the queue, and we could sort of see how little is working with that. We've already done that, but this is the 2 string for the for that server busy multiple simple sets time varying. And so what it does, notice that we didn't have to tell it how many we were going to hear. All we needed to tell it was what is the name of the state that you're going to hear index property events for. And so we had 2 servers here. And this is basically the data from the time varying. So this is how many state transitions there were. This is the minimum value. This is the maximum value. This is the one we're most interested in. This is the time average. And this is the variance and standard deviation, or, yeah. Variance and standard deviation here. So we see that the first one actually had many, many more state transitions. Now this count isn't the same. We can't sort of trust this as quite as much as we can for a tally. So for a tally, the count is exactly how many observations we had. But, so in this, because we were rotating them, their utilizations are actually fairly close, but we see that there were just many, many more state transitions for the more efficient one. And that means that since no good deed goes unpunished, basically because it was more efficient, it meant it had more services, because it would get done with its task sooner and then be available to do more customers. So, okay, so that is the implementation. And again, I will update with the right implementation at one, because this was just sort of one of the tests, just to make sure that it was kind of working. You know, say like okay, so